So we're here at the example table, and in this video we're going to be looking at some examples of antiderivatives. So, well, what's a derivative? If we have something like 5x cubed, we get the derivative here by using the power rule. The 3 comes down and multiplies by the 5 to give us 15, and then we have x squared, right? We decrease the 3 to 2. But we can also go in the other direction. We can say that 5x cubed is the antiderivative of 15x squared. It's the thing whose derivative is 15x squared. So, let's do an example. Suppose we're told that f prime of x is 2. What is f of x? Well, f of x is going to be the antiderivative, right? The thing whose derivative is f prime, or 2. And we know that the things that have a derivative of a constant are lines. And in this case, it's got to be 2x. The derivative of 2x is 2. Now, if we want to be thorough, we need a plus c on the end of this, where c can be any constant. Because if we make this 7, then the derivative of 2x plus 7 is still just 2. Right, so plus c makes this general. Let's get another example. Let's suppose that f prime of x is now this 2x. What is f of x? Well, this might look familiar. This is just the derivative of x squared. Right? When we take the derivative of x squared, the 2 comes out front, and this exponent is decreased by 1 to give us 1. What about something a little bit more complicated? What if f prime of x is 7x cubed? What is the antiderivative? Well, we have in the derivative an x cubed, and we know that that's going to come from something like x to the 4th. Right? This is how we're going to get an x cubed in the derivative. The original function needs an x to the 4th. Now all we need to do is figure out what constant to put out front. So whatever we do here, we want this constant to multiply by the 4 that comes down when we differentiate to give us a 7. And that constant is 7/4. Right? So when we differentiate this, we bring down the 4. 4 times 7/4 is 7. And we subtract 1 from this 4 to get 3. Right? But we need a plus c. Oh, and we need a plus c back here too. So that's how you do these general polynomial antiderivatives. Let's look at something different. What if f prime of x is cosine x? Well, once again, this is something familiar. We already think of cosine as being a derivative. It's the derivative of sine. So, sine of x is the antiderivative of cosine. Of course, don't forget the plus c. Now, what if f prime is sine x? Well, then the antiderivative, it's got to be something like cosine, but it's not quite cosine, right? Because the derivative of cosine is negative sine, and we want positive sine. So we need to throw a negative in front of the cosine. So negative cosine x plus c is the antiderivative of sine of x. Let's do one more example. Let's suppose that f prime of x is 3 over x to the 5th. Well, if we want to talk about this kind of function in a calculus context, let's do the thing that we almost always want to do, which is write this x to the 5th in the numerator. So we get 3 times x to the negative 5th. Now, what is the antiderivative? What is f of x? So we want to do the same thing that we did with 7x cubed. What will give us x to the negative 5th? Well, it's got to be an x to the negative fourth, right? Because up to some constant multiple out front, the derivative of x to the negative fourth is x to the negative fifth. What happens when you take this derivative? You bring a negative 4 out front. And whatever number we write here, we want it to multiply by negative 4 to give us 3. And that number is simply 3 over negative 4. Doesn't matter where you put the negative. Now, when the negative 4 comes down, the negative 4's cancel out. You're left with a 3. This negative 4 becomes a negative 5. So, negative 3/4 x to the negative fourth is the antiderivative of 3 over x to the fifth. Of course, we want to remember the c. Now, all these examples are relatively simple, right? Sine, cosine, a straightforward rational function, some polynomials before. And when they're simple like that, you can very often find the antiderivative just by looking at it. When things get more complicated, we're going to have to talk about more complicated techniques, and that will come up when we talk about integration.